Hi and welcome to Between Whiles. Today I would like to talk about one of the topics that fascinates me the most about astronomy, and it's the fact that every object in the universe seems to be rotating. And they don't just rotate around their own rotational axis, they also rotate around other massive objects. So this seems to be a very fundamental property of nature, that things just tend to be rotating constantly. In fact, this behavior of rotating objects is something that defines the very nature of galaxies and planets. And we usually talk about angular momentum, the amount of rotation that a system has. It's important because angular momentum is a conserved quantity, meaning that if you have a system and in the absence of external forces, that system is always going to conserve the same amount of rotation. So it's going to conserve angular momentum. This is called angular momentum conservation. But let's talk about celestial objects. They are the cool ones, right? Let's talk about astrophysics. Where is this angular momentum coming from? What in nature is making things rotate, right? There must be a mechanism that is making them rotate. So let's start with discussing the large scale structure. Let's start with galaxies. This is just a cartoonish version of the whole explanation because it's actually a very complex topic in astrophysics. So imagine you have these structures that we call protohalos of dark matter. They are spread around the universe at different alignments, different configurations, and different densities. Some of these clumps might be more massive than the others. But what they have in common is that they have dark matter. So these clumps of matter, of dark matter, are going to attract each other because of gravity. But because you have these random alignments and random distributions of mass, there will be parts in this configuration where gravity will be stronger. So then mass will be preferably going into that direction. Eventually, after you let the system evolve, the system will collapse gravitationally to a bigger dark matter halo, but it will have a net rotation. So it will have some amount of angular momentum. And this is pretty cool because that's exactly where galaxies are formed. Eventually, the gas collapses to the center of these dark matter halos and you form a galaxy that acquires the same angular momentum, or at least that's an approximation. So gravity rules. But remember that this is a cartoonish version. There are much higher complexities that we're not going to discuss. So this is in the large scales. This is for galaxies. What about planets? So in these galaxies, you will have a lot of gas and you'll have some molecular clouds that eventually, because of gravity, will collapse by themselves, right? But then you will have a similar thing happening as it happened in the formation of the dark matter halo. The gas will collapse, but there will be preferred directions. In the case of the gas inside a galaxy, there will be some tidal forces and some other things because they are already inside a lot of messy dust and gas inside the galaxy. But the overall effect is that some of these alignments will give you a leftover rotation of the star. So the star is going to be rotating at a certain speed. When you're forming an object that's rotating, it tends to form this flat disk around it because that's where you have the lowest energy configuration. So around the star you will have this disk of gas and dust, which is called the protoplanetary disk. Eventually, because of gravity, you will have clumps of mass coming together and they will form the planets. They will be rotating in the same direction as that disk that is around the star. So, for example, in our solar system, all of the planets are rotating in the same direction. Some of them will have their own moons, and we see that in our solar system there are hundreds of moons, and that's because many of them will go through the same process of formation due to gravity and due to the lowest energy configuration in the disk around the massive object. Okay, but that's the orbital motion around the star. What about their rotation? So in this animation, you can see that each planet has a different angular velocity, Jupiter being the fastest one. And almost all of them follow the same pattern. They are all rotating in the same direction, except for Venus, which is the only one that's rotating in the other direction. So you can see that the origin of rotation is just because of these chaotic random distributions of matter in the universe. You will have always some misalignments and some regions that have more matter than the others. That will eventually end up creating a system that's rotating. But all of them do. So moons rotate around their planets, planets around stars, stars around their galaxies, galaxies around local groups around large-scale structure, and maybe even the whole universe is rotating. Some surveys of thousands of galaxies have shown that there is some asymmetry between the number of galaxies that rotate clockwise against the ones that rotate counterclockwise. It's too early to say that this means that the whole universe is rotating, but this might be an indication that this is the case. So that would be pretty interesting. The angular momentum content of galaxies is a very fascinating topic because that's basically what makes them evolve, and that's what keeps them from collapsing. So next time someone asks you why do things rotate, you can explain to them that it has to do with the random distribution of matter and how things come together because of gravity. Thanks.